We have just covered the basics of motion known as kinematics, and now it's time for the counterpart, dynamics, namely the cause of motion. And it's called Newtonian from the simple fact that Newton is the guy that put it all together for us. 3 natural laws relating force and motion. Initially developed by Galileo Galilei, especially the first law, the law of inertia. And then Newton coming afterwards. Look at that. Born in the same year Galileo died. Well, forces push or pull. They can be contact, non-contact, which would be long range, like fields, gravity, electromagnetism. And the effect of the force depends on where they're applied. So for instance, here's some examples. And if I apply a force right here on this block, then based on the fact that it's applied at an angle, it's going to have a certain subsequent effect. It's going to result in translation. Over here in the middle, if we apply a force down like this with a pivot, a board with a pivot, you're going to get rotation, simple rotation. Over here on the right side, got something funny going on here. If I have a string attached to a wheel here and pull to the right, I can actually get this to go either rotate this way or the other way, clockwise or counterclockwise, depending on the angle at which that is pulled. You may want to ask me to demonstrate for you this kind of motion in class. In general, with forces, you can say that the resultant force is the sum of all the individual forces. It will always be true. And along with that, we have a condition called equilibrium. A condition in which a body can translate. Here you go. In case you're hungry, you can translate the cat over to a campfire. It can rotate. These gears rotating represent the way in which the engine translates power to the rear wheels on my diesel truck to enable it to go 0 to 60 in under 6 seconds. And both at the same time. Haha, isn't that cute? Raindrops translating, a shark rotating. Isn't that a happy camper with the umbrella? And aren't you impressed with the effective use of my 1990s graphics? All right. It's always true in equilibrium that the sum of the forces is equal to 0. Special case, meaning no acceleration. This is known as the first condition of equilibrium. Let's briefly consider the 3 laws. First law, inertia. In an inertial frame of reference, namely a reference frame that you are taking measurements in which the law of inertia holds, velocity is constant or velocity is 0. An object will maintain whatever motion it finds itself in, so whatever its initial velocity is, it stays constant. Unless the sum of the forces is not equal to 0. That's inertia. Now, in what sense is the surface of the Earth not a true inertial frame? The reason I would ask this is because the surface of the Earth is typically the reference frame from which we are taking measurements. So it's kind of a special case, but a very important special case. And the answer is the Earth rotates, so it has centripetal acceleration that is not constant velocity. In addition to that, it has mass, and therefore it produces, you guessed it, a G field. And a G field is indistinguishable from an acceleration, and therefore you don't have the conditions for true inertial reference frame. The valid categories are when you are at rest, constant velocity, or the special case, surface of the Earth, when you are in the condition of free fall. And the reason why being in the condition of free fall reestablishes that reference frame as being inertial is that you are basically eliminating the G field. If you are freely falling under the influence of gravity, then the effects of gravity in that reference frame you are in are not manifested. And when you do experiments like throwing a ball out away from you, it'll move in a straight line at constant speed away from you. And you will be convinced that you indeed are seeing the effects of the first law being manifested without fail. Actually, The alternative to that, being on the surface of the Earth and not being in free fall, obviously you throw a ball in front of you and it accelerates to the ground. You are essentially in an accelerated frame of reference. The second law, when the sum of the forces is not equal to 0. Under the conditions in which the motion itself is much less than c, the speed of light, so we're not taking relativistic mass increase into consideration. So let's not worry about that for the moment. So let's have an object. We'll call this object mass 1 with a force F applied to it. When that force F is applied to it, we can measure the acceleration. Then our next experiment is as follows. We double the magnitude of the force. And what you notice is that, in general, the acceleration doubles. That tells us a lot about the nature of the relationship between force and acceleration. Now let's make a larger mass, m2, or I should say just a different mass, and measure the force. And then actually apply a force, measure the acceleration. Well, when we do this, we discover, after doing these experiments, that the ratio of m1 over m2 is equal to the inverse ratio of the accelerations. It always seems to hold. Therefore, we can conclude, number 1, that the acceleration is proportional to force, and it's also proportional to inverse mass. And putting those two proportionalities together gives us that acceleration is proportional to force over mass. We can make the proportionality an equality by putting a proportionality constant in there, which by definition is equal to 1, and therefore we have F equals ma. Actually, sum of F is equal to ma. Now, before I go any further, I should probably just point out to you, in this first mass we were dealing with, obviously you see it's a TV screen. Now, you know I often ask you, or tell you basically, not to watch too much TV. It's a waste of time. But if you are going to watch TV, at least, please, at least watch something like this, which not only has a lot of intellectual content to build your cognitive abilities for calculation and analytical thinking skills, but moreover it holds a lot of, very good, solid moral content as well. So if you're going to watch TV, watch these kind of shows. Thank you very much. On to the next slide. So speaking of more precisely, we really need to break these forces into their individual dimensions, x and y. And then, taken together, we have the sum of the vector forces is ma. This is the net unbalanced force acting on an object in the x direction, y direction, z direction, and I suppose I could say etc., but we'll limit it to that. Conditions of the law, it's a vector equation. It's only corresponding to external forces, contact and non-contact, but they have to be external. Internal contact forces. If I stick an explosive device inside this object we're talking apart and blow it up, okay, I'll probably do that. But still, that won't say anything about the acceleration of the object, because all those forces, action-reaction pairs, oops, I'm getting ahead of myself, are equal and opposite. They cancel each other out in terms of any effect they have on the original object in the first place. So internal forces of no consequence. You can't get inside your car, grab the steering wheel and shove on it and expect your car to move forward, because then you're pushing back, your body will end up pushing back on the seat, etc. All right, so also m is constant. The number of particles is not changing, so you're not adding mass to the thing. And for inertial frame, it's an inertial frame under which this law is quantified and understood in the terms of how we're expressing it. So we have the MKS, or meter kilogram second system. In that system, 1 Newton will accelerate 1 kilogram at 1 meter per second squared. So if I take a kilogram mass and put a Newton of force on it, it accelerates 1 meter per second squared. The foot-pound second British system, 1 pound will accelerate 1 slug at 1 foot per second squared. Yes, the term slug is an awesome term, so embrace it and never forget it. A brief discussion of mass and weight. As soon as we discuss weight, we have to include the idea of gravity, of course. Weight, W, is force due to gravity. And that force in general is gm1 m2 over r squared. So here we have two masses, m1, the center mass right here, from that point to the center mass of this object that is in association with this entity, m2 separated by distance r. That force follows this equation, where the proportionality constant is very small. A freely falling space shuttle, once again under the influence of the gravity of the mass of the Earth, that force is equal to ma. F is equal to ma. A little more particular, you can think of that space shuttle having a weight equal to mg, g being the acceleration due to gravity of the Earth. So that again is gm, mass of the Earth, mass of the space shuttle, divided by the separation distance squared. Of course, masses go away, so we can get the strength of the g field of the mass of the Earth, which is g times that mass over r squared. This is equivalent to just saying that the acceleration is the force over the mass. That's the acceleration that's acting on that space shuttle. Then, in general, we can say, or perhaps specifically, that the acceleration is equal to the gravitational field, and that the centripetal force is equal to the gravitational force. And that is your starting point for all kinds of successful results in calculating orbital and space physics, the dynamics of orbits, etc. Now, mass can be expressed in terms of the amount of effect on the mass from a force. So we can say mass as a result of a force applied is F over A. That's known as the inertial mass, the effect of inertia, the tendency to resist motion. We apply force and get an acceleration. The ratio of those is the inertial mass. Let's take an equal arm balance. Here's an equal arm balance, and there is a mass on one side along with a known mass. Yep, that flea does not have a lot of intelligence. The unknown mass is the same as the known mass if they are balanced, because the gravitational tug on both sides is the same. Namely, the g field effect on these two masses is equal. So the gravitational mass is determined by the weight over gravity. Now, those are two ways of getting mass. Inertial mass, F over A, gravitational mass, weight over g. If you think about it, those are very different ways of determining the mass. One is the acceleration observed with a given force. The other is the weight that is determined by the gravitational tug. No motion involved at all. If you think about it, the particulars of how you're determining that are quite a bit different. You're not applying a force and seeing what the motion is. Okay. When we compare these two types of masses, we find out that the inertial mass is proportional to the gravitational mass. In fact, they're equal according to this proportionality constant c, and all attempts to measure what that value c is turns out to be 1 to any level of precision that we've ever been able to come up with. That may not seem like a very useful or important idea, but it actually is, and it led Einstein to his theory of general relativity, which has profound implications for not only just acceleration in general, but the actual development, evolution of the cosmos itself, the nature of space-time, the curvature of space, etc. And finally, the third law. You're all familiar with this. Whenever one body exerts a force on another, it's impossible for the second body not to exert a force on the first that is equal in magnitude, opposite in direction, and along the same line of action, not in some different direction. This is often called action-reaction pairs because they always come in pairs. Mathematical equation is simply the force of object 1 on 2 is equal to the negative of the force of object 2 on 1. I just say the same thing. 1 on 2 equals negative 2 on 1. There you go. Now, to just distinguish this a little bit, here's cart 1, here's cart 2. Let's have them explode. When they explode, there is a force of cart 1 on cart 2. So that's coming out here. And then we have simultaneously force of cart 2 on cart number 1 pushing to the left. Or you could think of it this way. We could have a collision. Cart 1 colliding with cart 2. Here they come. And when they collide, we have force of 1 on 2 to the right. Consequently, subsequently, concurrently, force of 2 on 1. All right. So in any collision, F1 on 2 is equal to minus F2 on 1. It's pretty self-evident, I think. Here's the Earth, here's the Moon. They are applying forces to each other. They are non-contact forces. They are field forces. Nevertheless, the principle is exactly the same. The force of Earth on the Moon is like this. Simultaneously, the force of Moon on Earth. The same size, opposite direction. How do you make sense of that? The Moon is a lot smaller. Okay, the Moon is a lot smaller. The G field is larger, so it pulls a certain amount. The Moon's G field is a lot smaller, but the mass that it's tugging on is a lot more, so its force ends up being exactly the same. Force of Earth on Moon is minus force of Moon on Earth. These are field forces. Now the third law is about action-reaction pairs. But we have to carefully distinguish between equal and opposite and action-reaction. It's the action-reaction that's important. So let's consider a small ant on a small table on the Earth. So A is ant, T is table, G is Earth. Those are subscripts that we're interested in. So this is the force of the ant on the table. The table applies a force to the table by pressing against it. I don't care how it's pressed against there, but it is, putting a force on it. Now, there's an equal and opposite force acting this way. That equal and opposite force is the force of the table shoving up on the ant. Oh, the ant was pushing on the table subsequently pushes back up on the ant. F ant on table is minus F of table on ant. That is an action-reaction pair. It's two objects acting concurrently with each other. One is a result of the other. One force is a direct consequence of the other. Now we also have force of gravity on the ant. Notice that that's the same size as the force of the ant on the table, etc. Same size, different force. Actually, that's the force that causes, subsequently, the ant to press against the table. But still, it's a different force. Force of gravity on the ant is equal to the negative of the force of the table on the ant. That's true. This force is equal and opposite to this force, but they are not action-reaction pairs. It's three different objects. The reaction pair counterpart would be the force of the ant on the Earth. The ant's G field tugging on the Earth would be the action-reaction counterpart to the gravity of Earth on the ant. So Fg on ant equals minus F ant on Earth. Right. G, of course, this may not look like it, but the G, of course, is from the Earth. I should say Earth on ant is minus F ant on Earth. There you go. And finally, a couple words about tension. Oh, be quiet. You guys are little chicks. You're not ducks. Anyway, ropes, cables, chains, worms subjected to pulls at both ends are said to be in tension. So we can consider a point along this worm. And To the right, we can say that's the force of the worm on the chick, and to the left, it's the force of the chick on the worm. So kind of looking at it from this half point of view here. The force this way is the force of the worm on this chick, and this way is the force of this chick on the worm. Okay, but that can be done at any point. Now the net force is 0 everywhere, and you can see that because of acceleration. So take any point along there, anywhere, and there's a potential infinite number of little cross sections that you could do this analysis on. The force of the chick on the worm equals negative force of worm on chick at any point. So here we have a rope, and in general, pick a point. You've got a force, and ultimately it's atomic forces that are being considered here. A force in the opposite direction. No net force, sum of F is 0, but nevertheless, the tension that it is subjected to is equal to the force F everywhere along that object.